Okay. All right. So yes, the code got fixed just by inserting this one line. RNG kind sample.kind equals rounding. This uses the old sample function. I don't know why this would fix the code, but I tried it and it made it work. Okay. So I don't know why the new sample function would break the thing. Maybe it didn't break and I just had to let it run longer, but something seems weird. Okay. So anyway, we've already done this thing where it goes through all the lines of War and Peace, and and it counts up all the letters and stuff. And rather than running through all of that stuff, I'm going to just I saved the results of that two-letter transition probability matrix, which looks like this, and this tells us that T followed by H is common, and H followed by E is common, and all of these other two-letter combinations are common, and this is how one way we evaluate whether the resulting words look good or not. Okay, and then we're going to just run some code here. Okay, and our probability is determined by two parts. One is the two-letter log probability. Okay, and this goes through kind of each pair of letters in the decoded text, and we say, well, how likely, or what's the likelihood that this was the original text? And we go through and we look at the two-letter transition probabilities, and if we see transitions like TH and HE, we say, okay, that seems pretty good. If we see transitions like FM and ZX or things like that, we would say those get low scores, right? So we're going to go through, and that's one way to evaluate the words, and then the other, or the original text, and the other part is we're going to use this lexical database that I'm not quite sure if it's fully accurate, but we go through each word that gets decoded, and we're going to go through the lines of text and say, if we find real words, we're going to give it a higher probability, and if we find nonsense words, we give those low probabilities. Okay. So the correct text is enter Hamlet, ham to be or not to be. That is the question. Okay. And here I'm just going to start at some arbitrary seed. Okay. And if we run this, what we're going to see is we're going to see the original text start off. Okay. And so let me scroll up, and what it's going to do is it's going to just swap two letters. Okay, and so somehow by using the old sample function for this part, it makes it work, and I really don't understand why. Okay, but we're going to just swap two letters. All right, and so in the beginning our mapping is terrible, we get all nonsense. Okay, but then we swap two letters, and then maybe after we swap two letters, we get more TH transitions and fewer, other transitions, and we say, okay, well, this, because it has TH, it's better than this other one, which didn't have any, right? And so, so we're going to do that, and we accept. Okay. Other swaps we propose will not be good, and we use the Metropolis algorithm whether we should accept or not. So we can still go in the, quote, wrong direction, into the direction of a less favorable swap, but it happens with not 100% probability. It's going to happen with a lower probability of going in the for a less favorable swap. But that's desirable, because if it says every swap has to result in an improvement, then you might get stuck at like a local maximum, right? So so we're going to say, yeah, we can take swaps that are not as good, but that's going to happen less of the time. And if we get a swap that's better than what we have, then we're going to take it for sure. Okay. And so the way that looks like is we propose the swap, we look at what text we would result if we use the proposed mapping after the swap. And we kind of combine the two likelihoods weighted, and we decide to go or not, right? And because it's log probabilities, we're going to generate a random U and log that and see if that's less than the difference. in the 2 log probabilities. Okay, so so this is going to do it, and we will see that it starts off with nonsense. Okay, so this is how it starts off. Okay, this is enter Hamlet to be or not to be, but it's CJMCP ATU VCM. That's enter Hamlet. Okay, and so we're going to start there. Okay. Oh, okay. I'm sorry. Actually, it comes in something else. All right, but you know, kind of right away, it starts swapping things. Okay, and so now we have at least some vowels here, and I really hope it works this time. It would be so sad if I said like I fixed it and then it still is broken, right? Oh, but look, we at around the 40-something iteration, we now have an E at the front. Right? This is a good sign. So what do we have? We have EN, so it's not enter, but it's Enaid Truhe. Okay, but we're getting better, right? Like this looks like it could be some language word, right? Doesn't look like English. Okay, all right. So now we have not enter Hamlet, but we have Enaid Shusha, and we're looking for enter Hamlet ham to be or not to be. Okay, so it looks like we got the E in the right spot. Okay, it's we lidnal al we instead of to be or not to be. But you know what it's doing is it's just swapping letters. Now, we are only seeing the outputs for the swaps that it accepts. Okay, and when it's taking a little while, what it's doing is it's proposing a bunch of swaps, and all of those swaps are getting rejected. And I'm not even bothering printing those out. Okay, and then we also know that when it rejects a swap, it technically takes the current thing and it samples it again, right? Like that thing gets repeated. And I'm not bothering printing those out because those would just be duplicates. Okay, so we're only seeing this get printed when there is an update. Okay, so, oh, look at this. We got to ented, krehet, kra, to we, odd, not to we. Okay, this is looking, that is the question, is the blestion, okay? But look, we got TION, that's like a big deal, okay? All right. Come on, computer, you can do it. All right. And I mean, at this point, like, we might, all right, so you know, we're looking for, that is the question, and this is supposed to be outrageous fortune, but it says old dageous fod something, okay. But it's, okay, we got the H. We got ented hackrit, okay? Hack to see, oh, we lost the, okay, well, we never had the B there. Okay, to see, odd, not to see. That is the blestion, wethef tis knocketh in the ring to some of the skinnies and the affos. I mean, it's kind of funny, right? It's like, we got the R. We got the R. This is like the most excitement we've had all quarter. Okay. All right, so we have enter Halet. Halet, to see or not to see. That is the question. And I don't know if we'll get the Q. But I mean, at this point, it's. I would say we're doing pretty good. We're doing pretty good. Okay. So it's just swapping 2 letters at a time. What do we get? We had what for a second? Oh, we had question for a second. Look at that. Oh, breaking my heart. Okay. You know, and it's just picking 2 arbitrary letters at a time, right? And so we're hoping in one of these things it's going to switch the Y with the M. And but you know, there's 26 choose 2. That's 26 times 25, 13. I don't know how many that is. Okay. Enter Hamlet, right? It's like everything that we get. It's so okay. So you know, it's whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against, so we have tave arms against a sea of troubles, not truckles, and I don't know what the CK is, and by opposing end, I think. Okay. I think we can let it run longer, and it might not get fully there, but I feel like at this point we can figure some of this stuff out. And I think part of it is because my lexicon isn't 100%, because I think if I looked up troubles, it doesn't appear in the lexicon, and truckles doesn't appear in the lexicon. So, but we did get it. We did get to be or not to be. Okay, and now we're, okay, and question is with a C, all right? But you know, at this point we're pretty good, right? Enter Hamlet to be or not to be, that is the question with a C. CU is, I guess, more common than QU in the entire English language. Okay, whether 'tis nobler in the mind to sever the slings and arrows. We got it. We got it. Okay, all right, we haven't gotten to tave arms against a sea of troubles and by, okay, oh, we lost it. Okay, opposing end, I don't know what, okay. So, all right, but good job, computer, all right? All right, I'm gonna go ahead and stop it. It will keep running for a long time, but it was kind of fun to look at all of this stuff. You know, in the beginning, it was just gibberish, right? It was just, you know, that almost looks like a bad word there. You know, VG, QVJ, you know, I don't, something, all right? But immediately, right, we start swapping letters so that rather than all vowels, I mean all consonants, like the first swap we took said, okay, let's throw some vowels in there, right? And then when the words with vowels show up, and so these are still like very much wrong, but you know, the initial swaps are all just like, let's get some more vowels in here, okay? And then we start moving things about to get stuff there, right? And I think this is a neat case of the Metropolis algorithm, because if we think about the target probability distribution, okay, it's a little bit strange to think of the mapping as coming from some target probability distribution. But again, there's 26 factorial possible mappings, and most of them are like very close to zero probabilities, okay? And there's only a few that have a reasonable probability based on how we've defined it, right? The one, like this one where we have question with a C and question with a Q, like the correct mapping will have a high probability, and then some that are like kind of adjacent to it, if there's a concept of adjacency here, will also have high probabilities, right? Like it's possible that it wasn't Hamlet to be or not to be. He could have said, you know, whether 'tis, you know, maybe because we have no concept of English structure, you know, if tave and take are both words that appear, or, you know, tame or something, some other word here, we might accept that, all right? And so, so those are the ones that have higher probabilities. And so what we're trying to do is we're trying to, quote, draw samples from this distribution of which the ones with high probabilities will appear. And the beauty of the Metropolis algorithm is that you can start in some arbitrary location where the initial conditions are absolutely terrible, but the way it's structured is that the probability of moving is the probability of the proposed divided by the probability of the current, and so the ones with better probabilities will be will be accepted, right? And the other great thing about this is that the true probability distribution is some function, I don't know, f of x, and if we integrated this across all possible values of x, I guess it's discrete, so it's not an integral. So if we sum this across all possible values of x, okay, and there's 26 factorial of them, we're going to get 1, okay? But the thing is we don't actually know what this function is, right? There's some complicated thing, and all we know is that f of x is proportional to kind of our p of x, all right, or whatever function we've decided, right? And we said p of x is going to be equal to basically the log probability of kind of the two-letter transitions plus the log probability of the real words, okay? And so this thing, f of x is proportional to this, but it's got some mystery constant that we don't know, but the Metropolis algorithm only requires the function be proportional. Only requires we have a function that is proportional to the target. Okay, and that's where we write min 1 probability of the proposed divided by probability of the current. Okay, and that's and so if there were some constant here, right? So there's some mystery constant here. Okay, these cancel out, and so we don't actually have to worry about those things, right? A function that is proportional to target, because if we say f of x is equal to c times p of x, then f proposed divided by f current is c times p proposed divided by c times p current, and these things cancel. Okay, so even though this constant is unknown to us, it doesn't matter, because in the Metropolis algorithm, the probability of moving only requires things that are proportional. Okay. All right. Okay, so that is that's our deciphering thing. And again, things can be improved if my lexicon was more accurate, included plural words, which is a significant deficiency of it right now. And so if we had a better lexicon, it would probably work even better. Okay, but it seemed, I don't know, I thought this was kind of neat. Okay, all right. I figured I would go back to the detailed balance stuff that I was talking about earlier, and let me just pull up kind of where I left off, which I think was right here. We're talking about the midterm. All right, so this is what I had said. All right. Okay. So I realized there's a few more a little bit more that I could say about this, because I didn't actually finish the kind of derivation or the proof here. Okay, so if there is a detailed balance, this is what we have, right? So this is the amount flowing from xk to xk plus 1. So right, if you just imagine some kind of oops. Right, and each of these things, you can kind of go back in on itself. So you've got some kind of chain in different states, and if this was x super k and this one is xk plus 1, what we want is that the amount flowing from xk to xk plus 1 and the amount flowing back, if these two are exactly the same, then these two states are at equilibrium, and we want this kind of for all the states, for any two states, if the amount flowing from one to the other and the amount flowing back, that's equal, right? Okay, so the amount flowing from xk to xk plus 1, if that's equal to the amount flowing from xk plus 1 to xk, then we have detailed bounds, right? And so the amount that's flowing is going to be kind of the probability of being at xk, all right? So we can think of this as kind of like the population of the island, all right? The probability of being there times the transition probability. So when you have the transition matrix, transition probability of then going from xk to xk plus 1, right? So the probability of being at xk, this is the probability of xk, okay? And then the transition of actually going there, okay, this can be broken down to kind of the probability of proposing times the probability of moving, right? So probability of proposing, that's going to come from our g of x. This is xk plus 1 given xk. So if you're at island 3, what's the probability of proposing island 4, okay? And then the probability of moving, which is going to be kind of like using the Metropolis algorithm or Metropolis Hastings algorithm. It's the minimum between 1 and kind of the p proposed divided by p current. Times the, for the Metropolis Hastings, you have to then balance this out by doing this. Xk given xk plus 1 and xk plus 1 given xk. Right? Is that okay? Sorry, this is a lot of text there. Right? So the probability, the amount flowing is, first you have to be on that island or be at that state, and then we're going to multiply it by the transition probability of going from that state to the kind of the adjacent state or the next state. And then we want this to kind of be the case for all pairs of xk and xk plus 1. All right, so that's what I have here, right? So we have, so first I said if we propose some new value x star and we reject it, then it's trivial because xk plus 1 is xk, and so the probability of going from xk to xk plus 1, which is itself, is going to be the probability of going from itself to itself. Okay, so that's a trivial case, right? So if you reject it and the next state where you end up is itself, then the probability of going from itself to itself is the same as the probability of going from itself to itself. So that's trivial, so we're not even going to bother. And so this is where we left off. We said let's look at this transition probability, okay? This transition probability, which I had just written on the previous slide, is the transition probability of going from xk to xk plus 1 is the probability of proposing xk plus 1 if we are at xk times this probability of moving using the Metropolis Hastings algorithm, which is basically p proposed to xk plus 1 divided by p current, p of xk, times kind of that adjustment factor, which is the Hastings part of the Metropolis Hastings, which says what's the probability of proposing xk for xk plus 1 divided by the probability of proposing xk plus 1 divided by xk, right? So if we know how the proposal distribution works, then that proposal distribution, if it's more likely to propose certain values than other values, when it does propose those rare values, we're going to give it more consideration. Okay. So that's what we have, and so I'm going to just kind of start. Starting here, we'll go ahead and work out the rest of detailed balance, okay? Okay, so what we want to show, okay, so if we work this out, okay, the next thing I can say is that okay, so I'm going to distribute, okay, we will distribute this through the minimum, okay? And I'm also, okay, so what I'm going to do is, let me just write in kind of over here, I'm going to, I distribute g of x, k plus 1, g of x, through the min function. Okay, and then I will also multiply by basically 1, but I'm going to multiply by the fraction p of xk divided by p of xk. Just slide this down here. Okay, so this is going to become the minimum of, so I have 1 right here, okay? I'm going to distribute g of x k plus 1 divided by, given x of k, okay? And then I'm going to multiply this by probability of x of k divided by the probability of x of k, okay? So this thing is equal to 1, and I think I'm allowed to do that, right? And then if I, okay, I guess multiply by this, or maybe I'll just say I'll also replace the 1. Instead of multiply, I'll say I will also replace the 1. Sorry, maybe not, multiply is not the word. With this, okay. So that's what I have, okay. And then over here, when I multiply by g of x k plus 1, okay, this thing cancels out with this down here, right? And so this is a little okay, and this will cancel out with this, and so now I have g of x k given x k plus 1. All right, so I'm going to just kind of rearrange a few things, and so the next step I will do is just, we rearrange terms, and then I will factor out 1 over p of xk. Okay, factor that out. All right, and so I have this transition probability, so the transition probability of going to xk plus 1, given that I'm at xk, is going to be equal to 1 divided by the probability of xk, okay, times the minimum of, okay, and so what do I have? I've got the probability of xk times g of xk plus 1 given xk. Okay, and then over here, I factored out p of xk, and so I have probability of xk plus 1 times g of xk given xk plus 1. So this is what I have. Okay, so so this is where I end up. So this is what I have. Okay, and then if I use the same logic, okay, so using the exact same steps, okay, I can also get the opposite, okay, the opposite transition probability, which is going to be the transition of going to xk. So I can also get kind of the opposite transition probability, right? And so I'm going to just, every place I see an xk, I'm going to replace with xk plus 1. All right, so this is going to be the probability of xk plus 1 times the minimum of the probability of xk. Probably should have used different letters, but I'm sorry. So this one's xk plus 1 now. Okay, every time you see an xk, replace it with an xk plus 1. Every time you see an xk plus 1, replace it with xk. So we're going to have g of xk x. I mean, you could do this on your own, but this is what we have, okay? All right, so this is what we have. So we have the transition probability of going from xk to xk plus 1, and we have the transition probability of going in the opposite direction of going from xk plus 1 to xk. Is that all right? Okay. And what we want to do is, if we use the target distribution, so the target distribution is P of x, and apply the transition probabilities. Okay, we want to see detailed balance. Okay, that is, okay, you need to show that probability of xk times the transition probability of going to xk plus 1, given that I'm at xk, is equal to the other thing, okay, which is probability of xk plus 1 times the transition probability of going from xk plus, I'm sorry, the xk, given that I'm at xk plus 1. Okay, so that's what we have. Okay, so let me do this. I think, actually, all right, let me just try, so this is the transition probability of going from there to there, okay. And so, so here I'm going to have the probability of starting at xk times the transition probability is equal to, and I'm going to just shrink this down and erase this. Okay, and I'm going to do probability of xk. Yeah. So I have this, and so these two cancel out. Yeah. So now I just have the resulting. This resulting thing is just the minimum of this thing. Is that good? Okay. And then okay, let me open the other one. Where's the other slide? Is that this one? Okay, so and then so the other transition probability is this, right? So and then the other one, kind of the other amount flowing. So kind of amount flowing from xk to xk plus 1 is this, and the other amount that flowing, which is xk plus 1 to xk, is going to be the probability of being at xk plus 1 times the transition probability of going to xk, given that we are at xk plus 1. Okay, so this, I'm going to copy this thing. Where is my snipping tool? So copy this. This is what we have here. All right, and so now I've got the probability of xk plus 1 times this thing. Okay, and so so this cancels with this, and we have this. Okay. And what we see is that we've got the minimum of this and this. And notice this. Okay, this thing is exactly equal to this thing. All right, and then this side is exactly equal to that side. So once you take, you know, kind of your starting probability of being at xk, or xk plus 1, and you multiply it by the transition probability of moving to the other state, those two things are exactly equal. Okay? So we have shown, okay, so the two terms are equal. That is to say, the probability of going from xk times probability of being at xk and then transitioning to xk plus 1 is equal to the amount flowing the other direction. Okay, so therefore we have balance, or I should say detailed balance, for any two states, xk and xk plus 1, okay? And this applies for both continuous and discrete cases for the Metropolis Hastings algorithm. And then the Metropolis algorithm itself is just a special case, and it actually makes this even more trivial, is that this this thing is just symmetric. Xk plus 1 given xk is equal to xk given xk plus 1. That's what it means to have a symmetric proposal distribution. And so if we have detailed balance for Metropolis Hastings, we have detailed balance for the Metropolis algorithm itself, right? And so, so we have detailed balance here, and then just to kind of, you know, say that the Metropolis Hastings algorithm will work in the long run, okay? So if we go back to kind of the ergodic theorem says that a Markov chain that is irreducible and aperiodic will eventually, again, the keyword is eventually, converge to its stationary distribution. Okay. And what we showed is that kind of our detailed balance thing shows that the stationary distribution, where the transition probabilities are determined by the Metropolis Hastings algorithm, will be equal to the target PDF, right? So if we create our transition probabilities using the Metropolis Hastings algorithm, our stationary distribution is equal to the target PDF or PMF. Okay, and so so that just means running this Markov chain for long enough will produce values from the sample that we want. Okay. Great. All right, so on Friday, we'll start looking at multivariate situations. Okay, so far we've only been dealing with kind of one variable at a time. And then on Friday, we'll start looking at multivariate situations where you have a target distribution that's in higher dimensions, and that makes things harder, okay? So we'll do that, and we've got some strategies to handle those situations. All right, we'll see you then.